Okay, so let's start again. So I wanted to summarize some things I said this morning, and particularly I had a question about this delta function here and exactly how it works. So just for the massless representation, what's going on is that you see from the asymptotic symmetry that the Fourier modes transform like this with I omega tau, and tau is the super translation. But you want to think of this as a BMS action. So BMS actions means that you have this pairing, abstract pair, which is now an infinite dimensional pairing between a super manta and a super translation. So if you want this integral to be equal to this one, you need the super manta to be a delta function. And where is this delta function pointing? It's pointing at the direction of the null momenta, right? So your particle has a null momenta omega z bar. Well, this super momenta is a function on the sphere with a delta function at that point. Okay, so it's slightly confusing with the delta function, precisely for the massless case because due to this delta function. In the massive case, will be very clear what the super momenta is. Yes. Well, it's hard. Okay, so here we call it hard. Yes, it's closely related to soft theorems as I'm going to try to convey now, but it's hard. We call it hard because for the reason that it's genuinely the situation where you start with a usual Poincare particle. It's just that you declare that actually it's a BMS particle. Okay, so in that sense it's hard. It's like it's a usual one. Oh, but yeah, okay, it's BMS. So it almost looks as if you have done nothing. Okay, so this is hard in this sense. There is the wave function is the same. Everything is the same. It's just that now you have an extra symmetry acting. So in this sense, it's hard. Okay, so let's do the same now for massive particles. Where is my... Right, so now, so the Carrollian field for the massive case is this simple A of y of exponential minus I ms, where here we have to remember that P, the massive momenta is M times this P tilde of K well, this is what it means, of Y. Well, what am I doing? This is what you mean. You evaluate this A on the point on this particular. You're identifying the hyperboloid at time like infinity with the mass shell of the momenta, and okay. So as we said, so translations are just translation in the fiber. So translations is just S goes to S plus P this tilde P tilde of Y. Okay, here let me insist. What this means is P mu is square root of 1 plus Y squared Yi. This is this object. And now, so translation is just you take this object and you contract with the translation. So it's spatial shift in the internal S fiber. But now you can extend it to super translations, so BMS. By doing the following, you take S goes to S plus omega curly T of Y. Now, it's a function on the base parameterized by 2, where you obtain this function. Well, it's important. Where? So this omega 2 of Y, you obtain by you want a super translation, T z bar. Well, you integrate it on the sphere against a propagator, which is this Q of z bar, contracted with P tilde of Y, and this is this object, to the cube. Okay. So from your super translation through, you can think of this guy as a boundary to bulk propagator going from the bulk of the hyperboloid to the hyperboloid. You're constructing a function on the hyperboloid. And you shift S by this function. Okay? So you might wonder, why is this natural? Okay, I mean, if you just want to see BMS representation, the statement is that this is what you should do. This is how you realize super translation on Thai. If you want to see it appear in some natural geometrical way, either completely Alada explain you that you can go asymptotically and look or do some change of coordinates and see how BMS transformation acts, or you can try to geometrize this. I mean, there is a sense in which this is some sort of symmetry of the Carrollian geometry on Thai, but it's not so illuminating, I think, so I will skip that part. But so if you want another way of saying this is that you can write the algebra of vector field for BMS as this omega to y of ds plus chi I di, and where this is isometry of the hyperboloid. So this is isometry of H3, so SO31. And now this guy is a usual BMS super translation. Yeah, so it's a realization of BMS as a infinite dimensional algebra of symmetry of Thai. No? And now with this we just act on our field. So it's just a shift in the exponential, and what we find is the massive hard representation. So we have phi of S y is now mapped to phi of S plus omega 2 of y. And in Fourier modes, this is just a of y is mapped to exponential I m integral d to z of curly t z bar divided by q z bar dot p tilde mu of k of y to the cube a of y. And this representation, okay, I should cite for correctly. So this representation in this form was really guessed by Longhi, Materazzi, as Joachim pointed out early on. I think it's 99. And this representation goes back to Sachs, who was the first to realize that you can do this. But here in these forms, there is nothing manifest what the super momenta of the representation here, because it's exactly in this form already. And so you can just read curly p from the integral. So this is curly p. This is now just curly p. So here the dictionary is we had the momenta p mu, which is m, so some mass, and this p tilde here of y, and we are mapping it to a super momenta p of z zeta z tilde bar, which is 1 over q de zeta bar dot p tilde of y. Mu and mu squared. Okay. Okay, so is the logic clear? So these are two we discovered, so to speak, uh, that there are two very specific BMS representation, and you can either realize them in terms of asymptotic symmetries, so again, or in terms of this abstract representation theory. In terms of asymptotic symmetry was due to Campilli-Alada, but this, in terms of representation, it goes back to its Longhi Materazzi, really. And in the structure is the same. It's always this integral with curly P contracted against curly T, and it's just that the supermomenta have different form. One is distributional, the other one is not. Yes? Okay. So, very good. So this being said, let's discuss a bit more of representation theory and what this says already and what we can say here. So these representations, these supermomentum, they have very specific properties that is worth discussing. And I'll try to relate these two sub-theorems by the end of the lecture. Okay, so we already discussed what supermomentum are. There is this just I want to insist on this, right? What I'm telling you here is that there is a map taking a massless momentum, well, a massive momentum here to a hard massive momentum, and then another map taking a massless momentum to a hard, to a supermomenta related. Okay? So this is some map here. What's very important is that this map is nonlinear. I will discuss soon, but there is something which is linear, which is a projection. So let me first talk about this. There always is a projection. So because this, when you're looking at the supermomenta, it looks very, this seems to be rather intuitive. It's usual momenta. These supermomenta, they are not so intuitive. However, we can always project one to the other. Projection of supermomenta to momenta. This works as follows. So suppose there is some nice supermomenta that you like. So by this I mean it's a weight minus 3, or well, delta equals 3 density. You can project it. I'm going to write it pi of mu. You project it on its momentum. So this is the momentum of the supermomenta via these projections, which is completely invariant. Okay, what you do is you just integrate it against this Q mu object from the beginning. It's absolutely not manifest from the way I'm explaining things that these things is Lorentz invariance, for example, does not depend on coordinate, etc. But it does. Nothing depends on any choice here. It's an invariant statement. So this is the momentum of the supermomenta. In that case, everything match, and we can go back. So that's the property of hard momenta, hard supermomenta. Is that, for example, for the massless one, if you do this pi mu of this curly p, z bar, this curly p, gives you the momenta you started from. Let's just work it out for the massless case, just to see what you see what I mean. It's very, so you start from p mu, so example, you start for p mu, it's massless, so you can write it as omega q mu z bar. You construct the supermomenta, curly p, well, yeah, p of zeta bar equal omega delta zeta minus z. Well, here it's completely obvious that now if you compute this projection, P mu of P is integral over d zeta bar of omega delta zeta minus z times q mu. Well, you recover omega q z bar. Okay, so there is this projection which is invariant, and the hard supermomenta, they are such that if you project on the momenta of the representation, you recover the momenta you started from. It's less obvious for the massive case, but you can check that it also works. Okay. So, okay, that's a general feature of BMS representation. Okay, here, these representations are very special, but in general, whenever you have a supermomenta in a BMS representation, you can always project over its momenta. In particular, you can always compute the mass of a representation, makes sense. And yeah, this is something you can always do. It's just that, again, these representations, they are very special from that perspective. Because it allows you to go the other way around. It lifts a momenta to a supermomenta. This is very special. Okay, so this projection allows to make sense of little group of BMS little group and Poincaré little group. So just because I want to be able to say in which sense these hard representations are special. So so definition. So BMS little group well, in the same sense, what is the little group? It's the stabilizer of the momentum. So it's stabilizer of curly P. And the Poincaré little group. So this is a subgroup of SL2C, subgroup of the Lorentz group. The Poincaré little group is the stabilizer of the project of the momenta associated. So it's stabilizer of P mu of curly P. Again, subgroup of SL2C. From the projection, one always have that the BMS little group. Well, I don't know. Well, stab of curly P is inside the stabilizer of P mu curly P. Okay. So this is always work. Now there is something very special about the hard representation, is that these are essentially, it's almost a characterization, not quite, but almost. They are essentially the only representation with the following feature. So hard supermomenta have the property that BMS little group, that both little group coincide, that both little group coincide. Yes, it's a very strong property. A priori, a supermomenta, the stabilizer of the supermomenta could be zero. Most of the time, if you pick a generic supermomenta, the BMS little group will be zero. However, when you project on its momenta, the momentum will always have the Poincaré little group. So most of the time, for the vast majority of BMS representation, this subgroup is very small, and it's strictly inside. Yeah, in print, this is but for the hard representation, there is something very special happening, is that both little groups are the same. It's almost a defining property, an abstract defining property of this representation. but not quite, but almost. There is a subtlety. For the massive case, it is a definition. So I mean, you can prove that there is the unique massive momenta such that satisfying this property is this one. This is defining property. For massless case, there is one extra possibility, so it's not as nice, but it's almost a defining property. Okay, so now I want to call. So what do I want to do? I think I need one more blackboard. So I'm just going to. I should write it the same. Tabar. Okay. However, from this projection, there is another class of supermomentum which is of interest that we'll see as some is what we call soft supermomenta. Said to be soft if its projection is zero. So this would give you very, very strange representation. So these are like zero momentum representation. So if you were to think of them in terms of Poincare group, the corresponding representation would have zero energy, zero momentum. So I think that's why they deserve the word soft. They would be a little bit more justifying the name later on. But this is the definition, but there is another nice characterization. Is that being soft is equivalent to the following. So these have to be distribution satisfying the following property. You can always write them with some curly n of z bar for derivative of t for some m. Okay. Your soft supermomenta if and only if there exists some n such that actually the distribution acts like this. That if you were to take t, if you replace t here, the curly t par t mu q mu, so by a translation, this will kill this guy. So soft supermomenta are the one which annihilate translations because of these four derivatives. The intuition is that this is exactly the differential operator which kills translations. Translations inside supermomentum, they are objects like this. Okay, but this is polynomial degree 2 in Z and Z bar, this object. This is just a bunch of Z bar, something like this. So this object is polynomial degree 2 in Z and Z bar. Translations are polynomials degree 2 on the celestial sphere. So this differential operator is the one annihilating translations. So that's the intuition. So this guy is soft in the sense that it annihilates all translations. Okay, but because it has zero momentum, this should be the zero. The momentum is zero means exactly this, that it's annihilating translations. Okay, and therefore, because of this property, I'm going to write the following. We will write curly p equal d to the bar squared n. Okay, but you have to be very careful, right? For soft momenta, for soft super momenta. Okay, so this is a reasonable notation because this is really what you mean by the derivative of a distribution. What you always mean by derivative of a distribution is this, right? If n is a distribution, this is the derivative of a distribution. So it's a legal, legit notations. However, you have to be careful because it's slightly in tension with some identities that you have seen in the literature. So you have to be careful. So this is really a derivative in sense of distribution. This means this. Okay. So in particular, maybe you've seen. Let me just stress this because at some point we might be confused. This is dangerous notation. This is careful. So because if you look at this, you might, and I'm sure a lot of you've seen in the literature the following, since sometimes you want to write the delta function in terms of bunch of derivatives. Where is that? Yes. Z minus zeta equal dz z bar of some log. Let me write this here. Okay, and there is a sense in which this distribution, this is correct, but there is also a sense in which it's incorrect, because certainly if by this you mean this, it cannot be correct, right? Because delta function against 1 is 1, and this annihilates constant. So it's dangerous. I mean, these notations are slightly dangerous. You have to be careful about what you mean. I always mean this, that I have a distribution which plays like this. Delta function is never a distribution. This is not a distributional equality. There is a sense in which this equality is correct, but not as distributions. Another way of saying this is that if you want to plug this equation inside the integral, you need to integrate by parts. And this guy has a singularity at z equal infinity. So it's not correct. You can't integrate by parts the z and z bars without being very careful about what you're doing. Yeah. Yeah. What's wrong is that you need to tell against, this is a distribution. So you need to say against which test function you're integrating. This is what is dangerous about this expression. What I mean is that this is a super momenta, so I'm always integrating against weighted densities, and they have very special behavior at z equal infinity, and you have to be very careful about that. So let me just show you the type of problems you might encounter if you take this too naively, is that suppose you integrate against 1. Then this is 1, but then this cannot be correct, right? Because, well, what's going on? Let's see it. 1, you integrate by parts, you have 0. Right? So it might seem that you have a problem. You don't have a problem. This guy has a singularity at z equal infinity. So the right thing is you integrate by part and you have a boundary term. So what I want to say, another way, this is correct, but this is not, doesn't mean that delta function is soft. Doesn't mean that delta function is a distribution like this. That's what it means. Because there is a boundary term at z equal infinity. So it's just a matter of, yeah. Okay. Any other discussion on this? So why am I saying this? Because one thing which is, I think, I believe, well, it's in some sense this was Strominger intuition in the first place, that the well, I mean, the point about this distribution is that they are not stable on their additions. So let me insist on this non-linearity of R supermomentum. So we pick some momentum, P1 mu, P2 mu, and we define P3 mu to be the sum, P1 mu plus P2 mu. So 3 momenta. And we consider the P1 ZZ bar, P2 ZZ bar, P3 ZZ bar, the corresponding supermomenta, the corresponding hard okay. So this is one thing we were discussing before. So if you're just thinking of the field themselves, it seems that you can always think of your usual Poincare field as a BMS representation and that it costs you nothing. Okay, it's just, okay, you're just allowing for BMS to act, then what? What did you gain new? This is what you gain new, because before, you could just add momenta and have momentum conservation. But now you're having a problem. So if we add the out supermomenta now, P1 plus P2, well, okay, you get P3, but not quite. There is another term. And surprisingly or unsurprisingly, depending on your intuition, the term that you need to add to compensate addition of out supermomenta is essentially the subfactor. So I think that's an important point. I mean, this is what tells you that that looking for BMS representation is not an obvious fact. You start with Poincare field, you think of them as being BMS representation. It seems that it costs you nothing because you're just, it's the same field, everything is the same. Yes, but now just having momentum conservation does not ensure that the hard particles do not scatter into each other. There is a piece that you're missing. And this piece is soft, and this is, in general, the subfactor. Yeah, so in general, you have sum of pi mu equals 0 implies that sum of the curly p I z bar equal to do square. I think there is a factor. I think I'm missing a 1 over pi factor. It's minus 1 over pi squared. Minus 1 over 2 pi squared. Anyway, it doesn't matter really, but yeah. Okay. Maybe I should say. So this Q is, skip this. Maybe I shouldn't have. So super translations. So invariantly, super translations, they are weight 1. Well, I'm going to write them like this. They are weight 1 conformal densities. Or minus 1, depends how you count. And there is always an injection of translation. There is an injection Lorentz invariance of, I should have said it before, I'm sorry, R31 inside. So there is an injection of translation inside super translation, and I'm realizing by, in coordinates, I'm realizing this injection by this Q mu z bar. Okay, so it looks like some coordinate object that I introduced in the first place, but in fact, it's a completely invariant geometrical object which is realizing this abstract fact that is always injected into super translation. That's why this object is everywhere all around the place. There's just some invariant object which is here. It was also this guide that I used to define the projection. I mean, actually, the fact that super momentum project on momentum is the dual picture of this one. You know, translation inject inside super translation, the super momenta in the dual, and therefore you get a projection. Okay. Yeah, I know. Otherwise, so I mean, what I'm trying to do here is write explicit expressions, but I'm aware that here and there it might look like completely not invariant, and you have no idea what the objects are. But okay. Yeah, now we can try to play to write to relate with soft theorems. I mean, it's almost there. Huh? Just this thing is already almost there. We can try to quantize the hard representation. That's a nice exercise. And in effect, it's not much more than the usual quantization of Poincare field, but still nice exercise, I feel. So now we declare that these are operator, that the P, they are operator. And we can write now the super momentum generator. So by quantizing, I mean we want to realize the BMS generators as operators on the space of fields. And this is, let's write it like this. I think you should recognize what you. So. And indeed, everything is the same as in your usual. It's just that now, you know, it's a super momentum, so it's a function on the sphere. It's a super momentum operator, but apart from it, it's so by the way, it looks like you get the usual momentum operator by your projection. So P mu at is just, well, you project P mu of this curly P. Let me do it just for the sake of the exercise. So P mu was integral over d to z of q mu z integral d3 pi 0 over pi 0 of barely p z bar a dag of p a of p. You permute the integral, and you find what you want. By definition, this is P mu. And so you recover the translation generators that we are used to. So now you can try to work this out and see it for the Carrollian fields, and you'll get something close to the Campilialada type of expressions for the charges. Yeah, I should write the charge. So this is the super translation generator. Now what we usually write is the charges Qt, and the charge is just now you integrate your super translation generator against the super momentum operator, right? Yeah, so this is like P mu, T mu. Okay, just to get a flavor of what's going on, let's do the massive and massless case here again. So as I've been told, ask at some point in this picture, it's like you're having different boundary, one for Ti, one for Scry. You have a bunch of momenta going here and here. So for massive fields, so let's start massless. So for massless field, this object, so hard. So I'm just going to plug in there what's the definition of the hard massless supermomenta. So it's this P over, so this is, in this case, this is omega d zeta bar, yes, times omega delta z minus zeta a dagger of P A of P. Delta functions localize these things, and we recover omega d omega squared a omega e omega of a dagger omega z bar a of omega z bar. Now and then if you use the dictionary with Carrollian field, you will just find the new square, the usual du phi u z bar to the squared. So just to see how all this works out together. So this is the usual R generator. This is the new square term that we have in usual BMX type of flux, and this is the usual energy. But now, again, this is a super momenta generator, so it depends on this bar. Yes. Yes. Yeah, there are two of them. One omega is coming from here, one from here. I think so. You can also see it from here. You have two derivatives, so one omega coming from each of the derivatives. This is due to the fact that this measure is bringing an extra factor of omega. So the measure itself brings first omega, and then you have the energy itself here. So this is the super momenta as seen at Scry. And you can try and see what it does for the massive fields. For them taking back this one. Yeah. So in this case, P mu is really M P tilde mu of K. Therefore, and this is the 3K divided by square root of 1 plus k squared. Yeah, and then a dagger of p, a dagger a of p divided by this q z t bar dot p tilde of k to the cube. There is an m cube in front. Yeah, and here you can just replace this by the Carrollian field without any trouble. So this is just this 3y square root of 1 plus y squared of phi of y, yeah, phi s of y, phi divided by and this is the expression, the sort of expression, well, yeah, that you find in Campiglia-Lada for the charges for massive fields. Right? So again, charges you obtain by integrating this against a super translation. Okay, so with this you can try to plug it in the S matrix and see what happens. And we'll have but as you might expect, we are going to have a problem. So we consider a process with P1, blah, blah, blah. Something happens, then it gets out. Momentum is conserved. But these are hard states. They are usual particles. So hard states. So we want to consider, yeah, P1, blah, 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 S of Pn, which is just insertion of these hard states. A yeah. And so now we want to ask, can we insert the this super translation generator P hard inside? However, we can check that with the definition, everything works out in the sense that this P hard commutes with the operators, P prime, right, to give you the hard supermomenta. A. And therefore, this means that this is equal to sum of Pi of the bar of P1 S of P I. And so this amplitude would be known. We would like to say that PMS symmetry is a symmetry, but just from what we started, it cannot, because this is non-zero. This is trying to impose conservation of supermomenta, but this is non-zero. This gives you precisely Weinberg's subfactor. So the point again is that hard representations, so that, I mean, this is in the sense that they are hard. You start with usual Poincare particle. You leave them to BMS particles. You think that you're not losing anything. It's true, but you cannot conserve supermomenta with such states. You cannot. So if you were to just construct an S matrix just with these states, well, it cannot be BMS invariance just because there is no way hard states can preserve supermomenta. So let me. Okay, so one finds that scattering of usual hard particles cannot be BMS invariant. But as you know, the solution, I think it's not the solution. I think it's if I had given this lecture, I think before Strominger, so 20 years ago, 10 years ago, I think we would have stopped. We'd have said, okay, no way. There is no way that the S matrix can be BMS invariant. Impossible. The usual states, the hard states, which are our usual notion of particles, they cannot preserve supermomenta. So that's it. We stop. BMS is not a good symmetry. It's over. But somewhat it's not. The surprise actually is that there is a sense in which it is, and this is. And this, as Strominger told us, this has to do with gravity, but it means that we need to change our notion of states. It means that the states that we've been discussing, the representation that we've been doing up to now, they cannot be the end of the story. So yeah, however, gravity will add a twist to that. Gravity. So, and by the way, I think so. Yesterday, Carlo told us that, remember, trying to construct some classical observables. You start with some QFT process, then it's infrared divergent, but you don't care. You regularize, you go through it, you compute a classical observable, great. But then you realize that actually the S matrix element that you had in the first place, when you take the regulator for your zero, and zero as a solution. And this was, I think, Strominger's main insight that he claims, that's the idea. I think it's very suggestive that the reason why, at the end of the day, when you take the regulator to be zero, this amplitude, you get zero as an amplitude is because of this. It's because the usual states, before you regulate, to use usual states, hard states, and they just cannot do the job. So somewhat this is a regulator. The regulator that you're using, in a sense, and here in Carlos' talk was by doing dim reg. In a sense, it's deforming what you mean by notion of states. You're going away from your usual particles. But when you're trying to take the regulator to zero, you're back to actually trying to compute this amplitude, which is zero. Okay. Sorry? Well, as far as we know, yeah. So the solution is that classically, well, yeah, classically for gravity, as I will write, what you want to call the super momentum generator is not this hard piece that I wrote. There's another piece. This other piece you can interpret as insertion of soft gravitons. That's exactly what it will coincide with soft surrounds. And yes, so it's gravity. So from that perspective, this is where gravity comes back. So I think we had this discussion with Xavier again, and yeah, this is where you need gravity to dynamically interact with your field to not have a zero here. You need some, and this is the soft gravitons. That's the usual intuition is that soft gravitons will make sure that the BMS charge can be preserved in the dynamical process. Yeah. Well, okay. So maybe I should say all these sort of stories about representations here, you could play with asymptotic symmetries of QED, these sort of these things. You would have other infrared divergences and other type of similar problems that you would need to cure with soft photons or soft gluons or these sort of things. Yeah, so for gravity, Carrier field, as we know, is this asymptotic shear. And the flux, I think so, yes.
So far, we were considering just bulk pure right?
Yeah.
So, I don't know, why is the story working so well without gravity and somehow here we need to add some perturbation and some gravity for things to work?
Well, the way I'm trying to tell the story is the following, is that you start with your state, usual Poincare states, you go to scry. You realize that for free, you can declare that they are BMS representation. So you're happy. Oh, good, now actually, a bigger group of symmetry, great. But now you're trying to use that symmetry to constrain the dynamical process. And you realize, well, that just with those states, they will never be able to fulfill super momentum conservation. So actually, you thought that you had BMS for free, but you don't. There's no way you can have BMS conservation unless Strominger comes in and tell you, well, you can, but now you need to add soft gravitons. But soft gravitons, we know by definition, somewhat, they will have to go away from this representation I described. They have to be something else. They cannot be part of your usual Fock Poincare state. They are something else, which is taking you away from your usual state. Does that make sense? Logic? Yeah. Yeah. Yeah.
And so, like, is it that this representation is not a robust result, but the way the symmetries are acting on representation is considering wrong, or is it that, like, really we shouldn't be thinking of these states as only kinds of non-linear representations, and we're going to actually, modify, I guess, things on the reduction side, like.
I don't know. I think that's sort of the open question. I think there is no discussion about, there's no discussion that usual Poincare states, they are these hard representations. I think there's no discussion about this. And they are, but we realize that they are not enough. And yet, Strominger tells us that the BMS matrix is, the S matrix is BMS invariance due to soft gravitons. So yes, I agree. I think the only way out is that you need other BMS representations, which are not those hard BMS. Yeah, but then you are opening a Pandora box because there are infinitely many of these other BMS representations. You need to work out what's the physics, what they are trying to tell you, all these sort of things. One intuition is that they maybe are a nice basis for some sort of coherent states, some sort of Faddeev-Coolidge states. Maybe these other representations, that's what they are, but I think this is to be worked out. I mean, you're really opening the Pandora box. I think that's one of the, but that's my, I think there is no discussion about the fact that from this perspective that I described, that you need to go away from the usual hard representation. And also we know this. I mean, we know that the usual Fock space is just not big enough to have these soft modes. The insertion of soft gravitons is immediately away from your usual Fock space. You're doing something that you should not be allowed to do when you do this. And yet, you need to do this if you want soft theorems to be implemented. So it's telling you that you need to go away from the usual Fock space. And this is not so much of a new idea. This is what Faddeev Kulish had been doing. It's what a lot of people have been doing back in the days. You need to modify your asymptotic states. But what I'm describing here is another way of forcing you to go away, but also telling you maybe what you should try to be doing. Look for these other representations and try to understand what sort of coherent state they are describing. That's sort of the message. Yeah. Discuss if I have this other representation, what we know about them, what they look like or not. Yeah. But so the usual solution to this problem, well, usual Strominger solution to this problem is that, yeah, in fact, the flux of BMS charges, so the BMS generator, so the BMS charges as a soft part now is of the form is yeah, Q, the curly T equal minus 2 0 T2Z, curly T, mu squared, and ZZ, and Z bar, minus 2 DZ, and Z bar. So classically, this is what you should use to generate the symmetry. You need to figure out what's your favorite derivation of this. I think Simone gives some derivation, but then there's also always some sort of twist and subtleties that you need to figure out for yourself, I think, in those things. But this is not what I want to discuss. Yeah, and then if you Fourier transform this thing, so yeah, so by the way, it means that the supermomentum generator, well, you're just taking away out this integral. Let's call minus 2 du and zz plus 2 gz squared and c bar, and then you plug in you expand this in terms of Fourier modes, and you find 1 over 16 p cube over omega squared d omega of a plus a plus a minus dagger minus, so this guy, yeah, so this guy, which is the hard part, plus now there is another contribution, which is 2 derivative of this operator, the limit as omega goes to 0 of omega a plus dagger plus a minus. So this is somewhat the surprise that's from the perspective of what they explain. This term is a surprise. This is the hard generator that we expect. But this is something else. And gravity seems to tell you that this is what you should include in your process if you really want to generate if you really want the supermomentum generator. And indeed, when you include this guy in the S matrix, gives you a new term that you interpret as being the missing part in the conservation of supermomentum. So now 0 equal P1, blah blah blah, curly p of z bar Bn. Now you rewrite as yeah, well, there was this sum of hard supermomenta. What is this? Yeah, I want to commute with the S matrix. This sum of hard momenta, which doesn't want to be zero, but now it's okay because you have insertion of a soft gravity on the other side, so you're safe, and your amplitude can be non-zero. A of omega. Okay, and I'm very schematic. I'm not too interested in having all the factors right. It's not too much the point here. Okay. And yeah. Yes. Then you have two contribution, right? So there is a factor 2. You need to be careful. Well, yeah. But you get a factor of 2, huh? Right? Yeah. This one, you mean? This one? That you're only taking. Yeah. Mm-hmm. So you mean if your soft gravitons is aligned as a collinear limit with some of the initial, these sort of things? Yeah, yeah. Okay, yeah, yeah, that's right. Yeah, if we wanted to be careful with this, probably, yeah. Okay, so yeah, is there a comment on this? So I think, well, yeah, and this, this becomes Weinberg's soft factor, and then you're good. No? Okay, so from the perspective of this lecture, again, you see, you're saving BMS symmetry, or you're discovering BMS symmetry, but the price to pay is that you need to include new states which were not there in your Fock space before. So maybe, as Carlo told us, maybe in fact you should not care. You should just, these states they cause infrared divergences, but you should regularize them. You don't see them, and then it seems that at least any of the classical observable you can compute does not depend on this. But still, it means that this amplitude is going to have trouble as a fundamental object. The amplitude itself is infrared divergences. I mean, as we know, this divergences comes with a one loop infrared divergences, and this is the real problem. And yet, yeah, this is a conceptual difficulty. And this lecture suggests that what you should try to do is include other type of states, other type of BMS representation. So now let's try to discuss a bit what are the other BMS and what maybe we can, how far can we go? Yeah. So generic BMS representation. So here by generic, I mean the non-hard one, perhaps also the non-soft ones, so any of them. So sorry, let me remind you the McCarthy recipe. That you should pick a supermomenta, curly P, construct, construct its orbit. Well, let me wave functions. Are functions on the orbit. So the orbit O of curly P is the space of all supermomenta. So let me call it K. This is some reference, curly K is some reference supermomenta. And so they are all the P's which can be obtained from K by acting with an element of the Lorentz group. It's M in SL2C. So in particular, so wave functions, they are function on the orbit. So we are going to have psi of, I don't know, P. They are C infinity functions, maybe probably L2. You want L2 function on the orbit of the supermomenta. Shit. But you see, since SL2C is finite dimensional, is 6-dimensional. The orbit is also at maximum. The orbit, the orbit is finite dimensional. And of the form, so O curly P equal SL2C quotiented by L curly P, where this is the BMS little group. Which is, well, I think I call it curly K. So BMS little group is the stabilizer of this reference supermomenta that I choose. So the orbits are finite dimensional because because they are discrete space. SL2C is at most 6-dimensional, so this is finite dimensional. So in particular, all these representations, they are always going to be, so we have L2 functions on a finite dimensional manifold. They are all going to be separable Hilbert space. So now the Hilbert space is the space of function here. So in particular, we get separable Hilbert space. So BMS representations are not that bad from this perspective. They are all separable Hilbert space. So not that bad. Okay, so you also need to choose spin. Well, yeah, so as in usual Poincare representation theory, you need to choose a representation of the little group, and let me not to go in that direction. What I want to like to emphasize is how different are those states, those wave functions from the usual functions. So now, since we have a projection curly P to pi mu, let me call it curly K, well no, curly P from pi mu of curly P. So we have a projection from supermomenta to momentum. Well, this orbit has a fiber bundle structure. Let me write it here so that we all see. And so, yeah, so the orbit of curly P is SL2C divided by the BMS little group, L curly P. Then I can project this, and it fibers over the orbit of, well, let me call it orbit of curly K. So this is the orbit of my reference supermomenta, and the BMS little group is the, yeah. And now I want to call K mu the reference momenta as the projection of the reference supermomenta. So here things for massless particle would be, for massive particle would be 1, 0, 0, or 1, 0, 0, 0, 1. And then, but so the orbit of the supermomenta now project on the orbit of this momenta, K mu, and the orbit, this is one of the usual mass shells. So it's L SL2C divided by the Poincare little group now, LK. And this LK is either it's the usual Poincare little group, so SU2 or ISO2 or SL2R. Okay. So what's going to happen is that these wave functions, they are not defined on bigger, higher dimensional objects, so typically dimensional. They are function on SL2C. They fiber, but they fiber over your usual material. This is usual momenta. And so you have extra degrees of freedom in the fiber. F is, so the fiber is typically the ratio of the Poincare little group by the BMS little group. And so these guys, these fibers at every point of your mass, so the picture you should have in mind of what is the BMS wave function is that you have your usual mass shell, but at each point of the mass shell you have extra degrees of freedom, which are written in terms of on which the BMS particle can feed. Let me maybe. Yeah, so not in particular, that for hard representation, as I told you, this is one of these very special case, almost definition again, where LK equal L curly K, and therefore there is no fiber. And thus, fiber are trivial. And we recover the usual mass shell. Okay, but in general, you are going to have extra degrees of freedom having to do with this more complicated, which tells you that the representation is more complicated. Okay, so you can try and play with this, but now maybe last thing I would like to say before concluding is how should we think of this, of a generic supermomenta? Hard supermomenta we understood. We started from usual point I field, go to scry, realize that PMS particles, well, we can see they're supermomenta. What's a generic supermomenta is going to, what is it going to be like? So let me write it as a proposition and then I will prove it. From what I've been done, it's almost trivial. So any supermomenta, so let P be any supermomenta, momentum, P mu equal pi mu of curly P be its momentum. And let P z bar be the hard associated momentum, supermomentum. Then one always have that curly P z bar equal P z bar plus dz bar curly. So you can always decompose any supermomentum into two pieces. It's hard piece and some extra soft contribution, and this piece of the supermomenta will tell you to which extent your representation is differs from the representation that we're used to. So if you just happen to do some sort of holography or whatever, where you have the BMS group as part of your theory, you represent it on the Hilbert space, gives you a unitary representation. What you need to do is work out what is the supermomenta of the representation. Once you do this decomposition, and this piece will tell you how far you are from actually considering one of your usual hard representations. The proof is almost trivial now, with the different result that I explained. So, by definition, we have P mu of curly P equal P, and by property of hard rep, well, P mu of P z bar equal P mu, thus P mu of curly P d z bar minus P d z bar equal P mu minus P mu equals 0. Therefore, this guy is soft. Thus, P z bar minus P z bar is soft, which means that it's equal for derivative of some distribution. That's it. Okay, and this is one last thing that I wanted to show you. So there is a sense in which, okay, so summary of what I presented these days. So as we go to scry or to time like infinity, we have this Carrollian geometry where the fields get induced. It seems that for free, you can think of that because now the asymptotic symmetry acts there. So it would seem that you get this symmetry for free, but not quite, because when you're trying to dynamically construct a dynamical process preserving the supermomentum, you realize that you cannot do this with usual representation, so you need to go beyond. And this is in some sense, this is what this is the content of sub-theorems. You need to go beyond your usual point, out BMS representation, and a generic BMS representation precisely is going to have some extra pieces deforming your representation. And in practice, what it does is that it creates internal degrees of freedom to your particles. Yeah, I think that's more or less all we understand on this right now. And I think there is quite a lot to be worked out to decipher what this is telling us. So yeah, thank you. Yeah. Yeah.
But what about the soft, massive super, those sub-theorems just deal with massless particles, right? So
You see, no, well, see, from the way I presented things, massive and massless particles, they are the same from the perspective of representation theory. I mean, you have two different massive hard supermomenta, but essentially their properties the same. They are different, but the properties they have is the same. And I mean, the soft gravitons, it's not so much that they are massless, it's that they are really gravitational. They are something else that somewhat we don't. I mean, from the perspective of the Fock space and representation, I think it's fair to say that we just don't understand what they are. But they are something that you're adding in the S matrix, and the soft theorem tells you that you have to add them. They are there. You have soft gravitons. They are something else. They are not your usual. Do not live in your usual Fock space, and you have to add them. And this is why. This is because the S matrix secretly wants you to add them. That in practice, in actual computation, you're adding all these soft gravitons to compute a finite, all-inclusive cross section. That you can have an actual S matrix, and that it can be BMS in. So this is what gravity is special from that perspective. It's not the thing that it's massless. It's the fact that it's gravity. Yeah.
Do the Melling transform of an amplitude
Yeah.
with a something, and this something, are you telling that it should not be BMS invariant because of the non-conservation of fluid momenta?
So I didn't say, because that would be wrong, I didn't say that the S matrix is not preserving supermomenta. I mean, the way the S matrix is preserving supermomenta is by forcing you to include soft gravitons. That's what it does. So the S matrix is no problem. Just that the way it does it, I mean, it should not be, because if you naively think that the S matrix is about hard states, it should not be BMS invariance. But the point is that the S matrix is forcing you to include extra states. And this is what makes it BMS invariant. So at the end of the day, it is, everything is BMS invariant at the end of the day. It's just that in order to do this, you need to include new states. You need to go away from the usual Fock space, which is just saying this is not very new. I mean, this is already IFADF Coolidge ideas, Keebles from the very beginning of infrared divergences. So yeah.
Should not be doing the Melling transform.
Yes, well, but yeah. Well, I think
Resulting object. Can you say something about BMS symmetry?
So, yeah, maybe if your question is how would I see a BMS representation in the celestial basis? Maybe that's your question. This, yeah, I think, yeah, I don't know. I think the point is that this is hard to see. The celestial basis behaves very strangely with respect to super translation. So if you want, I mean, actually, well, we know the answer is that one BMS particles on the celestial sphere is like an infinite towers of fields with different conformal weights. I mean, you need all of them to represent one state. So, yeah. So yeah, that's yeah. I cannot say much more. Yeah.
So before, I think maybe it's written that we gave a functional form to the determinant number of a delta function.
Yeah.
Okay. As you move away along the fiber, do you have also a functional form also for this new
So yeah, just before, just what I was saying about this delta was just a warning that when you write this, you should not think that you are allowed to take the delta function and hide it inside the n. That's what I wanted to say. It's not allowed because here I really mean derivatives in sense of distributions. That's really what I want to say. So this, I don't really want to say that this identity for the delta function is wrong. It's correct, but you need to be careful when you're using it, and it can be wrong or correct depending on on how you are using it. So yeah, that's all I wanted to say with this. Yeah.
Okay, but the question was,
Yeah.
as you move along the fiber,
Yes.
you stay,
Yes. Yes.
what's the subspace of distributions in which you
It can be very complicated. So let me give you one, maybe I think what you're asking for is an example. Let me just give you one example of non-obvious super momentum, but I mean, you could imagine anything, I mean, any sort of distribution. So a distribution is, for example, take what I describe as hard massive super momenta, plus you add two derivatives of a delta function, z minus z. It's the same delta function. If I want to be correct, I need 1 over omega and exponential, something like this. Anyway, this is another representation. The BMS little group is R2 in that case. And now you have an extra alpha because U1 is not in if this was just this is in this orbit. Now with this bit, the U1 in the iso2 and some U1, one is acting, and this is this U1 that I wrote here. So now you have an extra degree of freedom for your states. Yeah, and you can do a lot of sort of things. Another example you can try to do is you take another, let's say another, so this is zeta 1, you take zeta 2. This is another representation, different. You can do also, you can, all sort of distributions, I don't know. I mean, yeah, you see, the fiber is a submanifold, but it's a fiber of distributions. It's like this is a distribution, but really it's a distribution parameterized by one number and z. So this object really is just the usual null cone of massless particles, and this is an extra U1 on top of the cone, but the quantize distribution. No, it could be anything. You could really, you can do almost, it can be any distribution. But then you will get, it would be another representation. Yeah, okay, maybe it's easy. The fiber is like this. If you stay in this representation, but then you could have another representation, completely different type of BMS particles with, I don't know, now 4 derivative of delta. It's yet another, it's yet another. Oh, yeah, but if you stay in the fiber, you preserve this form. But yeah, that's about it. Yeah, please, yeah.